In this section, we will discuss the Newton's method. This is a good numerical approximate method to solve algebraic equations. In the first semester, we considered equation of the form fx is 0, but f was one real function of one real argument. It is easy to derive the algorithm of the Newton's method using the following picture. Consider the graph of the function f, assuming the function is nice, that means continuous and has continuous derivatives. And we want to find the intersection of the graph of the function with the x-axis. That means we want to find a number, the value x, for which fx is equal to 0, this point. Bad news is that for most equations, we will never see the exact solution in our life. But good news is that we can approximate the solution as close as we wish. The Newton's method works this way. If we have some initial approximation x0, we can consider the function value, that means the point on the graph of the function, and using derivative, we can build the tangent line. And while the tangent line crosses the x-axis, this will be a point, let's call it x1, the next approximation, a better approximation of the root. And then we can repeat this step on and on, coming closer and closer to the root. And how to find x1 when we know x0? We can write the tangent of this angle in two ways. First, this is the function value divided by the change of the argument, and also this is equal to the slope of the tangent, which is the derivative of the function at the point x0. And knowing x0, this is an easy equation for one unknown x1. Namely, if we divide by f prime and when we multiply by x0 minus x1, we have f at x0 divided by derivative at x0 is x0 minus x1. And then x1 can be expressed as x0 minus this fraction, f x0 divided by f prime, namely the derivative. Well, and this is the heart, this is the algorithm, this is the core of the Newton's method, and we can go on. In general, we can consider the next approximation, xn plus 1, being the previous approximation xn, minus this correction, which is in the form of the function value at the point xn, divided by the derivative at xn. And now, if we have a system of a system of algebraic equations, that means if we have f from Rn to Rn, this means that the function f has not just one but n arguments. That means n unknown variables, unknown quantities in the equation. And that means that f has n components of the result. Actually, we have n different functions. That means we have n equations. So n equations for n unknowns. This is important. It must be a square system, the same number of equations as the number of unknowns. Well, and in a very similar way, we can derive the algorithm for the Newton's method for a system of equations. Just instead of x, we have some vector x arrow. Instead of f, we have some function f arrow, set of functions. And instead of 0, we have a vector with zeros. Then such a graph is not easy to sketch for higher n. But the idea here was, instead of considering the complicated curve we consider just a simple straight line. That means instead of the complicated equation fx is 0, we replaced this complicated equation with a simple equation t1x is 0. Right? Because t1x is fx0 plus f derivative x0 times x minus x0, and this should be equal to 0. And when you subtract x0, when you divide by f prime, and when you add x0, you get exactly this Newton's method. So now, when f is no more one function but n functions, then for each component of f, we can consider one component of the Taylor polynomial. So as f is from Rn to Rn, so is its Taylor polynomial from Rn to Rn. And we will be happy just with T1, first order Taylor polynomial. So we have the vector Taylor polynomial for a vector argument and vector result. And then the function value at x0 at x can be approximated by T1. That will be f arrow at x0. Now f prime is the Jacobi matrix of first order partial derivatives. Let's call it J, which is the matrix, times, and this is difference of two vectors, which is a vector, and matrix times vector is a vector. So this plus is sum of two column vectors, and we have 0 on the right. And in the same way, we can find x0. We subtract f to get j at x0 times x minus x0 is minus f at x0. Now, instead of dividing by f prime, we multiply by j inverse, and from the left. That means j vanishes here, and we have x minus x0 is minus j inverse at x0 times f at x0. And if we add x0, we have the next approximation, let's call it x1, as x0 minus j, this is the Jacobi matrix of partial derivatives, at x0 times f arrow at x0. And then if we replace x0 with xn, we have here xn plus 1. So very, very simple, and very similar to the situation for one variable, for one equation. Just instead of x and f, we have vectors, and instead of f derivative, we have the Jacobi matrix of the first order derivatives, and instead of dividing by the derivative, we multiply by j inverse. Well, and again the question arises, how many steps should we perform? The advantage of the Newton's method is, if we are close to the solution, then the convergence is very fast. So some 5, 6, 7 iterations are usually quite enough. And we can compare how xn and x minus 1 differ, or we can compare how f goes quickly to 0. So in the next section we will illustrate this by some example.